I'm talking about computers, and this is a workshop about astronomy. So I always feel like I have to justify what I'm doing. And Mike, says, "Hey, computers are used a lot in astronomy." So that's the point, right? Computers are used a lot. That is true for the professionals. It's also true for the amateurs like myself. I confess that I use computers almost every waking minute. So when I do my own astronomical observations at night, I do it for fun. I tend to leave my computer off, just in principle. I'm not working. But lots of other folks who do amateur astronomy actually do it on the computer. So anyway, we're going to take a look at some of the way these things are done, and we'll extrapolate a little bit because, hey, why not? It's the right audience to extrapolate on, right? So here are some of the things that people might want to use computers for. And we start with controlling equipment, okay? That's kind of basic kind of things that you want. You want to automate things that are repetitive, boring, etc. And data processing in general. And finally, you want to deal with scientific models, okay? So we have some of that as well. Okay, so let's look at controlling equipment. There's some easy stuff in there, okay? For example, controlling a telescope. It used to be, as an amateur astronomer, I can tell you this, it used to be that you have to have your telescope kind of on an equatorial mount that could rotate opposite the way the Earth rotated. So you have to align it against the North Star to be able to get it to rotate at the right axis and so on. And, that's pretty cool, but that takes time to set up. So I guess I want to say, I'm probably wrong on this, but on the order of 15 years ago, maybe a little more, maybe a little less, they started building telescopes with motorized drives that are actually a lot easier to set up. And instead of rotating on an axis, they actually just go up, left, up, right, up, left, and so on to kind of compensate for the Earth's motion. And to do that, you need a computer, right? So even in kind of home equipment, you have that just for telescope control, right? And these things, of course, you punch in a button and say, go to this thing, and off it goes, right? So they're pretty cool. And we have vehicle control. Good example of that are the Mars rovers, right? So this is actually pretty old technology, okay? And this is a good thing. It's tested. It works. Originally done for manufacturing, because there you have these huge assembly lines that you need to put this here and that there and so on. And you have robots doing those for cars. I guess the Japanese started that. And now for almost any assembly line anywhere, right? You have that kind of robotic control. And what you want to have is kind of a mixture of hardware and software to be able to do this well, okay? Interestingly, at least for me, I kind of like history. So this goes back to cybernetics and Nord Weiner, who's one of my heroes. And he was writing about this, 20s and 30s, and talking about how this could come to pass and what it meant and what control theory was. Well, he didn't quite get to see it, but hey, it's there, it's real, it works, okay? And it can be very sophisticated. I mean, the basics are simple, but you can really go at it to make sure that you don't do damage to the thing. One of the other things I like to do is fly planes. So a lot of my examples come from that world. And in fly-by-wire airplanes, for example, you have controlling of the surfaces, the flight surfaces, is done through computers. And they actually take into account the forces that will happen to you if you move the control surface in that direction, given the current speed and so on. And so they'll prevent you from doing certain maneuvers that would otherwise, break your plane in midair. This is a good thing. Little planes don't have that, unfortunately. Anyway, there's some more kind of old technology. Telerobotics is the fancy name for what we call Waldos, right? And that's been around for quite a while. It's pretty effective. Neatest example, I told you, I fly. But to me would be the, quote, unmanned air vehicles, where there's actually somebody flying them. But the person who's flying them can be quite literally on the other side of the world. And that's got to be a rush. And anyway, Mars rovers are the most dramatic recent example of this kind of stuff. Being a computer geek, I like the fact that they run on this RAD 6000 board, mostly because it is so limited, okay? I mean, I think my cell phone has more compute power. That may not be entirely true, but it's really close. It's actually quite a bit by space mission standards, particularly the memory. They have a lot more memory than most space missions do, but still less than my iPod by an order of magnitude. Okay, stuff that I really like. The artificial intelligence aspect of all this, because that's close to my interest in computer science. And it's actually kind of neat. The Mars rovers, of course, are affected by the speed of light. They're pretty far away. So we might be able to control an aircraft that's on the other side of the world with no problems, but going to another planet, that'd be a little rough. So you need to have that machine be able to make its own decisions in a certain way, right? And that's what the rovers do. So what they actually plan, because AI just isn't there yet to be able to just set them loose on the planet, okay, is that at night you have human drivers, basically, and this is their title, and they will actually figure out how to drive this thing. And in some ways, what they're doing is they're writing a computer program that actually says, this is what I'm going to do tomorrow. It's a little bit more interesting than that, because even though it is a program, it still gives a great deal of flexibility to the rover itself, so that if something unforeseen happens, it won't just automatically fall into a ditch or something. And you take this program. I would hate to be the programmers. Actually, I think I would love it. It's living on the edge. But you run your program for the first time in another planet, and if you have a bug, you screw up in some way, you destroy this horribly expensive piece of equipment with everybody looking at you, right? Yeah, I mean, it's fun. I mean, this guy's had the best job in the world. But so one of the things they do is they simulate before they actually ship the software. They run it very carefully on Earth as best they can to make sure that it really will work in the field, and then ship it. I find it amazing that they managed to do it for as long as they have. Anyway, task automation is something that's important for us for a lot of reasons. There are some things that, quite frankly, you just can't leave to humans, okay? And I say that they're too important for that. And what can happen is that humans are by nature careless. And so we'll make a mistake every once in a while, not all the time, but every once in a while. And in some tasks, that's just not good enough. So you want to try to automate that. Things that are too boring kind of fall into that category. In some ways, for some people, like myself, if it's boring, it leads into making mistakes. So that kind of falls under both. Other people seem to handle boring, but on the other hand, as a computer guy, I kind of feel the need to liberate him and to say, no, you don't have to do that. Okay, this is the same kind of power that I think engineers had, right? When they said, no, you don't have to push that cart anymore. I got this motor that will do it for you. So, I think that'll be really cool. And then there's stuff that's just too time intensive. Even if we could do it and we wanted to do it, we wouldn't get it done. Here are some examples from astronomy. Searching for comets. This is one of the hobbies of a lot of people that are into amateur astronomy like myself. And I think one of the reasons that it's so popular is because it has a built-in ego boo. And this is how you pay, amateurs, right? So if you actually find one, you get your name attached to it. Instant fame, hello. So there's a lot of motivation for doing this. And actually a lot of amateur astronomers do this kind of thing. Something that I find absolutely amazing. I mean, I can't relate to this kind of dedication, I guess. But some of the die-hard comet hunters basically have memorized the way the sky looks in patches through their telescope, right? So at a particular magnitude, they know exactly what it looks like, so they can look at it. That way they don't have to take their eyes off the eyepiece to look at the map to make a confirmation. They just know what it is. And they feel that taking their eyes off will give the other guy who's hunting for comets an advantage, right? Of course, you got to be number one. Nobody remembers the second guy who found the comet. So, that chase is on, and they do this kind of stuff. Some guys really like it, right? Unfortunately for those guys, this is the kind of thing that's really easy to do with automation. because you look at a section of the sky, you take a picture, you compare it to a known picture of what that section is supposed to look like, and you go, hey, this is new. Hello, maybe we found something. It's not quite that straightforward, of course, because it could be new, but it could be something else, not necessarily a comet. But still, it's a lot easier than memorizing what the sky looks like at 10th magnitude or whatever, and going out there and checking. So that's done. Okay. I've seen predictions for the last 4 years that basically humans are going to get crowded completely out of the comet finding business because of these tools. I think it's inevitable that will be the case, although it still hasn't happened. Humans are still finding some. Anyway, we can also do that to supernovae, and this is actually important for real science. Again, like I said, I'm interested in history. This is the old way of doing this, where you took 2 photographic plates, taken at different times of the same region of the sky, and you look through a machine that can basically swap back and forth between those. And then you would see, and you would be able to tell, oh, look, here's something new, right? And those blinkers would be used to find things like supernovas and such. And again, it's the exact same trick. We can do that with computers really well. Okay, I haven't done an aside yet. And I do a lot of asides. So here's number 1. This is actually the same technique that people use for like security cameras. Okay? So you put a security camera here, and it takes a picture of the scene, right? At night, when there's not a lot of people in it, of course. Then when somebody walks in, you can essentially take the difference of the camera image with the empty image and go, oh, look, there's somebody right there, okay? It also works for detecting movement. So you take a picture, you take another picture at, half a second later. You subtract those 2 pictures. The only things that don't cancel out is where somebody or something is moving. So those are the techniques that we use in computer vision. All right. Let's look at the humaning aspect of computer science, and how do we actually make life better for people. And, well, I take that back. This is the opposite of that. What I'm trying to get at are things that someday we'll be able to do better than people, I believe, but today we can't. Okay? So we actually need human computation instead of just machine computation. Best example that I know of, although there's quite a few of these, is Galaxy Zoo. And I would use this example for any talk about this kind of stuff, not just for astronomy, because I really think it is the best example of it. But the idea is that you take these pictures and you show them to people, and then you ask them to categorize it in certain ways. And humans are just a lot better at that than computers, even today, okay? And there's folks over in machine learning that are trying really hard to bridge that gap. And I think they got a long ways to go. But the proof is that the professionals are saying, okay, we can't push the computers hard enough, so you guys that have a lot of free time, give us a hand. And interesting things have happened. My favorite little thing that's come out of Galaxy Zoo, and I don't actually know the resolution, but maybe somebody here does. Somebody looks at a galaxy and goes, hey, that's a really funny jet coming out of it. What is this? And people go, we have no clue. So they start getting the astronomers interested, go look at it and go, we still have no clue. And that was as of, I don't know, last time I looked at that particular incident was a few months ago. Might be resolved by now, but it's interesting. I mean, there's real science that's coming out of actually having human eyeballs looking at some of these images. Curiously, probably the first human eyeballs to look at some of these images, so that you can notice something different. That noticing something different, again, computers just not very good at. Okay, mostly it's because they notice too many things that are different, so they drown you out in the noise. Right? Okay, let's talk about data processing. Right. This is kind of the boring part of computers. Okay. And in my department, we kind of say, well, yeah, the business school teaches that kind of stuff, and leave it at that. But this is what made computers popular and affordable. Back to the random bits of history. In the old days, people thought that computers might someday have a market of about 20 to 30. Okay? And it was really a chance meeting between a manufacturer of computers and somebody who did airline reservations that kind of went, hey, we could help with that. And of course, the rest is history. So This is really important. You cannot underestimate it. Some of us have jobs because of it, so I'm a big fan of it. But yeah, boring. So anyway, you can do some of those same techniques really in exciting ways, like with astronomical data. And here are some facts, okay? Astronomy today is done primarily or exclusively in digital form, okay? You know, it's not the old Mount Palomar, you know, big photographic plates. You know, we don't do that. So you're taking your data from the telescope, you have it in digital form, and then you can store it and process it in lots of interesting ways. One thing the astronomical community has done is develop all sorts of formats, standard formats to store this data, and that's really important. Okay? So, kind of problems that they run into, that's a lot of data that they're trying to store and process. Okay? So, kind of the extreme example is survey data, which by its very nature is trying to take pictures of a fairly large region of the sky. You know, it could be at varying resolutions, whatever. These are two of my favorite, well, these are actually my two favorite survey databases out there, primarily because they're accessible to people like me, okay? So that's what I like about them. This guy's make your data to the public, and I mean, I would have loved to have been in their IT department, because what they have to do to support this is really, really amazing. So that's a fantastic project. SDSS makes its data available to the public through something called the Sky Server, which is available online on the web. Okay, it's just a web page you can go to. And I imagine they had some kind of a grant for outreach, because they have a lot of tutorial information that's really, really cool, and at different levels of expertise. Okay, so it has actually became kind of a portal for me, you know, just to find information. And you know, it has a lot of the images from there. These are some of the stuff that they give. The stuff that's in here is of interest primarily to the real astronomers, right? You know, other people can do stuff like show me the picture, right? And it'll oblige you and say, here it is. Okay, so you can go there and find pictures of just about any astronomical object you can imagine. Okay, it does have a very nice user interface to do that search. Okay, which is great. I mean, like I said, it's accessible, it's wonderful. It is an incredible kind of project. Okay, now I said that it would be difficult to do this. That is actually really hard. So let me give you a touch of that. The search facilities are probably, I consider, to be the most important thing that they need to provide. And they have a really nice start, but boy, there is room for improvement. And that is, that's just something that as a computer science professor, I look at it and I go, oh my God, there's research to be done, there are grants to be written. This could be really cool. Maybe someday I'll do that, I don't know. They store the data in a relational database, which as a computer scientist, I go, wow, I wonder why. I just don't think that was their best choice, but then again, maybe it was. I mean, I wasn't part of the design discussions. So they may have an excellent reason for it. I'll talk later about some things that I think might have worked better here than what they had. And in order to search the data, there's basically two ways of doing it. You can use those nice user interface tools that I described. Those are great for people like me, right? That just want to go, okay, show me a picture of Orion. Come on, ooh, show me a different one. On the other hand, for the real astronomers, they have to learn SQL, okay, which is a database language that goes back to the 70s in computer science.
Or their students have to.
I'm sorry?
Or their students have to.
Oh, their students have to, that's right. That's why God invented graduate students. So, you know, you need to do these. Honestly, I feel sorry for the students with that, by the way. Every talk that has to do with astronomy needs one of these. There's mine. So, back to the talk, SQL. SQL is fine, right? You know, it's okay, but it's just not very good. I mean, let's be honest. Actually, this past July 4th weekend, there was a revolutionary meeting in San Francisco. It had to be San Francisco, where computer scientists got together and are trying to overthrow the tyranny of SQL. I wish them luck. And they actually, you know, even though they took a somewhat facetious way to host their meeting, okay, what they're doing is real. And they included folks from Google and Microsoft and IBM and just a lot of people that are saying enough is enough. We need better stuff. But anyway, here's a very simple, and I do mean that, a simple query of what you might try to do from that digital survey. And whenever I look at this, and by the way, I want to emphasize this is a simple one. What I did was I went through their tutorial that said how to do the searches and picked the only one that would fit on my slides. Okay? You know, they get quite a bit larger than this. And it's like cruel and unusual punishment to send a poor astronomer off to learn this stuff. It's like, why? They have better stuff to do. I mean, even the computer scientists have better stuff to do than learn this, although it's a little bit more justified. So we need better ways to do this. So let's bring Google in, okay? The reason to bring them in is because the one thing they do well, and they really do this well, is searching, right? And like I said, that's kind of the problem that you need to solve. By the way, they do other things really well, like distributed processing, okay? They're fantastic at it. Like user interfaces. I think they're really, really good at that. So, you know, they have a lot of core skills that could be better used, you know, doing something with astronomy than searching the web. And so let's see what they could do. Actually, you know, they have so much money they don't quite know what to do with it. So they're solving part of that problem. They got together with one of the new survey teams and said, hey, let's do something. Okay, we're Google, we have money, you got a telescope, perfect match. This is the kind of stuff that these guys are doing. They're talking about generating 30 terabytes of data per night. That's a big number. Even for a computer scientist, that's a big number. And I just have no feel for those numbers, right? You know, once you get past 2 or 3 zeros, I can't relate. So yeah, you know, I mean, you guys worry about orders of magnitude, right? 2 or 3 zeros in the exponent. You know, that's the key. So for me, you know, I need something to make it real. And I don't know if any of you remember Ronald Reagan, but I thought the greatest thing he ever did was he tried to explain how much money was in the deficit, which by the way, back then was like tiny. And he explained it by stacking dollar bills, figuratively, of course, and you know, saying, well, these things would reach Earth orbit, right? And I went, oh, that's a lot of dollar bills, okay? That brought it home. So I try to do something similar. So it ends up being about 40,000 CDs, okay? So you can imagine stacking those. It actually about half of what the Library of Congress has. So the Library of Congress is still pretty big, even in those terms. It would take, you know, this survey 2 days to accumulate as much data as is in the Library of Congress. Then YouTube, I can't find any new data on this. When Google bought out YouTube, they got real quiet about their storage facilities. So this is the last set of numbers before YouTube was acquired. At the time, they had about 1/20th of 30 terabytes, okay? They had about 1.5 terabytes of storage at the time. I wonder what it is today, because it's been about, what, 15 months since they got acquired, something like that, okay? So that could be even more competitive now. But anyway, that's quite a bit of stuff. This is taken from their presentation on how they actually managed to do this. I have no intention of going through this, but the only thing that I want to kind of point out is down here you have the actual survey scope, right, which is generating all this data, and it sends it through a high-speed channel to an archive center, which is distributed, and then can send it to all sorts of different data centers, right? That's their architecture. That's how you manage that much data being produced in a single day, okay? So you have to distribute it. You don't keep it in a central location. And you have to have really fat internet pipes between your archive and your source. A not too different graph would actually show you what the Large Hadron Collider is doing over in Europe. They have a very similar type of infrastructure. They use different protocols because they're in a different continent, but it's the same kind of thing where you have the LHC here going to kind of the first level servers, okay, which collect the data, but mostly they pass it on to the second level servers, which can then do the storage. And you know, a researcher who's interested in part of it can then run a distributed query to collect it and have it sent to his or her location. So that's kind of how they plan it. Same solution, just a different space. Nobody knows how to do this any better. Okay, you know. So anyway, like I said, Google is doing this for them. I should have mentioned earlier that Microsoft actually did that with the Sloan. Okay, and I think there's a good reason for that. I mean, you know, computer scientists will like hard problems that have to do with computers, and you know, data management is pretty boring. It seems like, oh, there's nothing really to do there, unless, of course, you're talking about this much data, and then all of a sudden, ooh, there's lots of things to do there. So, you know, we're like hammers looking for nails. We'll go after whoever has the need to store that much data, and we'll say, can we partner? You know, let's do something, because this is fun. Okay. This is actually not the first time that Google tries to do this. Okay. They do. I mean, they do so many different projects. Okay. I think half the people in the company don't actually know, or at least work on search, right? Because they're all doing all this other stuff. So one of the kind of side things that they do is one day they looked around and they noticed that they had, I don't know, untold cabinets full of terabytes of space that were doing nothing. So they said, well, I wonder if anybody would want these. And they go, oh yeah, scientists. Yeah, they always need a place to store data. So they put out a press release and said, hey, if you're a scientist and you want to store your scientific data someplace, we'll store it for free. You put it in here and then other people can use it. Right? They don't have to go to your web page to get at this data. So a lot of the people that do things like gene sequencing, and I don't know if astronomy, but maybe astronomers too, but you know, there's a lot of data sets that have kind of migrated over to storage in Google. Okay? And it's kind of interesting. One of the problems that they have, or that the scientists had rather, was, okay, I've collected all this data and I want to now store it over in Google. The problem is that I can't send it over because you know, my department doesn't have the internet bandwidth to be able to ship this much data over the net. So instead what they do is they put it on a physical hard drive or several hard drives and then physically carry it over to their servers. That's known as the sneaker net, which is still the fastest way to move terabytes of data around the globe. Okay, so FedEx has high latency but very high throughput as far as networking goes. So go with them if you have that need. Anyway, Google has a lot of interesting technology. This is by no means an exhaustive list, but this is some of the things that actually apply to this kind of thing that they're participating in. So first one I want to mention is PageRank. The reason that this applies to this is because it's the reason they have money to spend on these kinds of things. PageRank was their solution to to build a better search engine, right? And actually it was my PhD advisor who one day said to me, you should try Google. And I said, Google, what's that? So, you know, it comes all the way from there. And what he said was they have a really cool way to solve the real problem with search. The problem with search, by the way, is not finding web pages. That's actually really easy. I mean, finding them is something that I could give my freshmen or maybe my sophomores to do. The real problem is ordering them. Right? How do you know which are the most important 10 web pages in the world that have to do with these topics? As opposed to, well, I found 3 million web pages that have to do with this topic. Here are 10 of them. Right? It's the ordering that's critical. And that's what PageRank is. The original idea was that if there's lots of links into a page, then it must be good. Right? I mean, that's the essence of PageRank. Surprisingly, it works well. I mean, they've tweaked it, but it works pretty good. Anyway, Google File System is more useful to what we're talking about. Google File System is the way that they store all of that data. I kind of like, I was once in a presentation by one of the Google VPs, and he made the offhanded comment, you know, the internet, yeah, the internet's really cool. We have 6 or 7 copies of it in my office. And it kind of gave me a sense of how much disk space they have. So here's how they do it. They actually have commodity machines. They don't have Dells by any means, at least I don't think so. But that's kind of what I translated to. Rows and rows of Dells, right? And one thing they do have is lots of bandwidth. Okay, that's where they spend most of their money. Their PCs are not very expensive because they're commodity boxes. They arrange them in groups. And the reason for arranging them in groups is that even if you have really fast internet connectivity, It's simply faster for machines to talk to each other if they're physically located nearby. So all of the machines in this room might be in a group, and they go to like 80 machines in a group. And then you have another set of machines over there and another set of machines over there. And the data is distributed across that system. This is different than the way most people would have organized it, and I think it's really brilliant of them. But rather than have one large database running SQL, for example, okay, that has all the web pages in the world, they said, wait a minute, just how big a machine are we going to need to host that? Forget it. We'll just spread that out across all these other boxes, and chances are that you're never going to need all of it in the same place, so we win big. That was their insight. GFS is the file system that makes that transparent so that you don't have to write software that knows that this is here and that's there and so on. And that's a huge advance. Okay. On top of Google File System, they implement something called Bigtable. Bigtable is basically their answer to the database, challenge. And what they said was, well, relational databases just don't work for the kind of things we do. So we're going to store it in a really big table, too big to fit in any one node. We'll distribute it across several nodes. You see how Google File System comes into play, right? And we'll let you query it the way that you would query a relational database, except not with SQL. They have other techniques. But this is actually pretty cool. It scales to petabytes. I mean, they do it. This is what they use to support the PageRank algorithm that I talked about earlier. This is also what they do for things like Google Finance, right, where they're storing all those quotes and so on. So, I mean, this is real. It's kind of a nice idea. And you can see how this is cool for something like astronomy that's generating vast amounts of data. MapReduce is their answer to the computation problem. Okay? We can use the Google File System or maybe Bigtable to store this large amounts of data. By the way, the difference between those two boils down to how structured is your data. If it's not very structured, if it's documents, right, then you can just use the file system. If it's actually structured, for example, a time stamp, a symbol name, and a value, okay, for like a quote system, then you can use Bigtable. That's what the difference boils down to. MapReduce answers computation. I have my data stored. How do I find what I'm looking for? How do I do anything interesting with it? This is what that does. And it's actually a very interesting programming technique, because the key to be able to executing your program over that amount of data, of course, is not to try to run the program on one computer, but to run it on several hundred or thousands if you can, right? And that's a very hard way to program. In my department, we don't even teach students how to program that way. We say, no, that's an advanced topic, okay? Other departments might approach it at like the senior level, right? They'll say, okay, so let's teach you about parallelism. You won't really need to know this, but just in case somebody mentions it, here's what it is, right? So it's just not part of the core computer science skill. So if I hire a programmer to come work for my company, they won't know how to do this. Well, Google had that problem. How do we solve it? They came up with a way of doing distributed programming that was actually accessible to a typical programmer, right? And that's really, really cool. The basic idea is that you take a small chunk of the data, and then your map operation works on that chunk of the data. For example, if your operation is to find links in web pages, then the chunk of the data might be 10 web pages, and your output then is a bunch of this page references that page, this page references that page, and so on. And then Reduce takes some of those result chunks and combines them in some useful way. One useful way might be take the union of them. Right, another useful way might be take the largest one, etc. Okay, and it's entirely under programmer control. That's how they map the web. Okay, that's what they do. Okay, so it's actually interesting that they make all this available for free. I mean, they just give it away. And at first I thought they're giving their secrets away. Are they fools? Are they idiots? No, they're actually very bright. What they're not giving away is how they run their data center. Right, they still keep that secret. So that's you try having thousands of machines running at all times.
Who said that?
There you go.
Who said that? The internet is great.
That was one of the Google VPs. I don't remember which one. But I was just at I wasn't paying attention, but I was at a place where he was giving a talk, and when he just made that offhanded comment, I went, oh God, that's too good. Okay. Anyway. Google is actually trying to convince the world that MapReduce is the way to do programming. And they're having pretty good success. Stanford actually has a course where they teach that to their freshmen, incoming freshmen. So these are people that, well, it's Stanford, so they probably already know how to program. But still, they feel that this is accessible to first-year computer science students, as opposed to a really advanced topic that maybe you see in your fourth year. That, I think, is excellent. And what they're claiming is that scientific computing can use the same techniques that they applied to the web search and have just really fast processing. So for example, that's kind of the basic concept behind cloud computing, which is also known as grid computing, utility computing, on-demand computing. It depends on who's selling you the solution for it, what name it is. These are all kind of the same term, but they're based on those kinds of techniques. There's other possibilities, but that's it.
Excuse me, I know that you've got a lot of material to get through, but could you explain cloud computing a little bit?
Yeah, I mean, cloud computing is this, maybe a better term is actually utility computing that shows what was meant by it. And what was meant by it was you didn't have to buy a computer so that you could do computing. Instead, you would use the utility concept where you don't have your own power plant to run electricity. When you need electricity, you plug into the wall. So when you need compute cycles to be able to run your job, then you plug into the wall and you actually get computers. I'm sorry?
Like having a terminal?
It's like having terminals to a central compute facility. Amazon, right, except instead of a really big mainframe, what we have now are a bunch of small computers, right? And that means that you can rent one computer for an hour or 1,000 computers for 10 hours or whatever you need. For some people, like let's take scientists that are doing deep computation tasks, they may have a fancy server. It's not doing anything today because I'm not doing a compute task. Well, they're still paying for it, right? But on the other hand, if you allow them to get as many servers as they need when they're running their big job and then not have any when they're not running their job, then supposedly they'll save money, right? That's the pitch. That's what cloud computing is.
Okay.
Okay.
I've gotten several explanations and they've all been needlessly complicated.
Okay. All right. So we're now going to tackle a dangerous topic, and that's geeks in love. Google, the Google engineers really love their technology, and this is good, okay? Everybody should love their own technology. But almost every technologist I know is in love with Google's technology. So this is like a really big love affair that's going on and is completely carried away. So Chris Anderson is actually a pretty cool guy. Does Wired. He recently actually suggested that Google would replace the scientific method. And when I read that, I went, oh, come on. No, I can't go there, okay? So I read his article, which I think was what he was trying to do, You put in a headline like that, you're bound to get readers. So his point boils down to this. You have all this data, right? You have petabytes of data that modern scientific projects are collecting. You can't make any sense of it, okay? The human brain just can't, right? You can't come up with a theory that explains it, nothing, because you can't even see the whole data set, right? And that's what the scientific method was all about. You see some data, you come up with some conjectures, and then you test them, right? So he's saying, well, that can't happen anymore. But then he goes on to point out, don't worry. It's not the end of science. It's just the end of the scientific method, because we'll use Google to analyze that data. And so we don't actually need scientists. For example, he says, Google does not have a theory as to why this web page is good. Instead, they just know that it's popular. That's good enough. We can do science that way. We don't need to understand why something happens. Google Tech will just tell us, look, this is happening. Bet your life on it. I can't go there.
Object.
Yes, I object strongly.
I, for one, do not welcome our new
I don't either. I think they're kind of, but they're really trying. This to me is frightening and kind of exciting at the same time. They now basically have so many processors, memory. This, by the way, is memory, not disk, terabytes of memory, okay? And, petabytes of disk space, that they're saying, look, we could actually model the brain, literally, one-to-one model of the brain. And then let's see what happens, right? So they're not kidding. I just don't like it. Okay, I'm a reactionary. I like history. You know, being a computer guy, I feel guilty. It's like I should be in love with this stuff, but I'm just not. Okay. Yeah, maybe model-less science would be okay for some things, but overall, I feel like, what's the point then, right? And you know, to me, it's about the models because that's what gives the explanation. That's what gives me a, you know, again, I'm going to swap into computer geek terms, but it compresses all these observations into 1, 2, 3, 4 formulas that I can understand, right? And that compression factor is critical for somebody that has a small brain, right? You know, I can't fit all the data, but I can remember a couple of formulas. So that's what you want. This is the ideal sequence that's taught in school, right? And I'm talking elementary school, high school, and so on, where you have, you know, Brock makes some observations. Kepler goes, I looked at your observations, and as far as I can tell, these things are happening. I don't really know why, but these things really are happening. Maybe that's the Google tech. And then comes somebody like Newton that goes, you know, gosh, nobody saw this earlier. I'll explain to you what this happens. You know, any other things for me to do? So, you know, that's the way it should work, right? By the way, back to artificial intelligence. There are actually some AI programs that fit in this scale. One of my favorite is a little program called Bacon. It is actually can go from Brock's observation to Kepler's laws by itself, just by kind of looking at the data and going, hey, interesting, I see this. It also does Galileo's you know, kinematics laws by looking at raw data and then going, look, here's a formula that explains that data really nicely. So maybe Google Tech won't do it, but who knows, maybe AI will someday give us, you know, robot scientists that actually advance science. I'm not sure if that's good or bad. I mean, I just know that it's something that might happen. Interestingly, I think models are going to make a comeback. Okay, I mean, not that they've left the scene or anything, but I think they're getting even bigger. It used to be that models were primarily or almost exclusively differential equations. You know, if you wanted to understand the world, you wrote down the differential equations that explained it, or integral equations in some cases. But basically, that's what you did. Here's my explanation of whatever's happening. And then you put a period at the end of it and said, that's it, okay? And you had to put a period because nobody could solve them, right? So you could explain the fundamental principles, and then you said, yeah, and if there's only one atom in the universe, then here's the answer, right? If there's more than that, we'll have to approximate it, and it's ugly, okay? So that's pretty much the state of the art, right? But anything that did not fit into a differential equations then was taken out of scope. We just don't do that, okay? But you can do it with computers. You can take those intractable models and actually solve them with computers by, you know, integrating them in a kind of a formal sense. And then you can look at the results even if you can't solve them directly. Now, mind you, there are huge uncertainties here, okay? But that's modern science. That's how we do things, right? So the obvious model to point to are the global climate models, right? Nobody can solve those, but here's the results of running them under this.
So I'm seeing more and more criticism of climatology in general because, and I think some of this came from Freeman Dyson, actually.
Yeah.
Just the notion that if you depend on computer models, it's not science, we can't trust it, period, without looking at it in detail, which I find ridiculous because I think we've learned a lot from computer modeling and it works. It may be complex situations, it doesn't work as well or as reliably, but there seems to be, as a function of this global climate change denialist position, to dismiss computer modeling as a scientific tool.
Right.
Wasn't there something a little while ago where they tried to model climate, you know, or weather? Maybe it was weather, and they he went to lunch or something, and he missed part of the program, so he came back and he reprogrammed it, but it didn't behave the same way.
You talking about chaos theory, or?
No, I don't think that.
Well, yeah, you are actually. It is the famous example of chaos theory. Is
yeah,
when he put in the data, and he decided because he was doing not quite sleepers in that, but actually re-keyboarding data, he just went only to X number of digits of significant data. When he reran the experiment, he ran a few more digits and got completely different results, and that's where we got chaos theory and the sensitive dependence on the initial conditions coming from.
Oh, my bad.
Yeah. One of the kind of
There's a similar situation where models are constructed by fitting historical data and assuming the same relation will hold into the future. And those sorts of models tend to be very good at reconstructing past conditions and terrible at predicting the future.
My mother can tell you that without a computer.
Yeah. So I think the point is, to me, the point is that if you can't validate the model, then you always have to take it with a grain of salt. It becomes no different than a heuristic.
Yeah. The climate guys really have an uphill battle, right? And one of the ways that they responded, and I'm not sure how good a science this is, okay? But it's certainly seductive. And what they've said is they come back to the notion of cloud computing. And okay, we need all these runs of the models, okay? And the real problem is that, like you pointed out, if you have uncertainty in the starting conditions, then you get wildly different results, right? So what we'll do is we'll run them for all possible starting conditions, you know. So I'm exaggerating a little bit, but they'll go, you know, okay, so x plus 10 to the minus 5, x plus, you know, and so on, and run that. Of course, you need way too much compute power. Nobody can afford it, so they ask for people to donate their spare CPU cycles, and they do. Then they collect all these runs of the models with initial conditions from 50 years ago. They look at what they predicted over the past 50 years. If it actually fits what really happened, and we have records of that, then we go, okay, that was a good run, and then you'll see what it says over the next 50 years. If it doesn't actually predict well what happened in the previous 50, then you go, well, that was a bad set of starting conditions, and you throw it out, right? And that's you know, that's how the IPCC has been doing the models more recently, and it's kind of interesting. You know, it's got a. I'm sorry.
It's also how the quants on Wall Street were modeling
Right.
the economy. And if you fail to correctly perceive the range of possibilities, or your weighting of possibilities is skewed by looking at a non-representative period of time, then your predictions, although they may be good while the same conditions hold, could be wildly off, as we saw on Wall Street.
And that's one thing that frightens me just a little bit. I mean, we saw the collapse of the market, and you know, Wired actually pointed the finger at this formula is the one that destroyed it, and said, look, and it comes out to an assumption as to the distribution of errors, which is nonsensical. And then they even found this is the programmer who implemented it, and it's like, oh no. So it could well be that this will ruin us. Oh, by the way, this is a model of colliding black holes. So you know, it's done in this actually with one massive supercomputer. But anyway, you have to have something like this in any astronomy talk. So that's what I have. You know, basically, computer tech is applicable to astronomy in a lot of different ways. That's not too surprising in the sense that it's been applied to just about anything in a lot of different ways. Astronomy just happens to be cooler than a lot of the other applications, so it's more fun. And the kind of speculative stuff is that there's new insight and new techniques that can be used to advance science. I genuinely want that to be true. I believe it at least half the time. And we'll see, okay? You know, one thing that I'm claiming today, and this is kind of a political battle, right, with other departments, but it's that the way that mathematics was in the 20th century, 19th century, that it was, you know, the handmaiden to science is what the language of science, that was true, but that the current language of science is computers. And of course that involves a lot of math, but you know, but that is the language of science, so that it wouldn't be unreasonable for somebody to say, here's my model of ecology, or my model of, you know, blood flow in the human body, or my model of, you know, God help us, oil through porous media or something, and it's a massive computer program. So anyway, that's all I have.
You know, as a practicing astronomer,